problem. 762 prime number of set base in binary representation. So for this problem, we are just need to check from the integers left to the right how many prime number of set base. So for example, for this number 6, the set base is 2, so it is a prime number, so we're gonna count it. For 7, it is 3, we're gonna count it. But for 8, it is 1, we will not count it because 1 is not a prime number. But for 9 and 10, we're gonna count it because 2 is the set base and 2 is a prime number. So let's just solve it directly. We're gonna prepare a result. So for I in range from the left to the right plus 1. So if it's prime, I'm gonna write it later. If it's prime, maybe I'm gonna use n. And for this number n, I'm gonna check the set base. Yeah. So this n gonna equal to I dot. In Python, we can use bit count directly to check for this number how many set base are there. So yeah, we're gonna use I dot bit count to check how many bits of number 1. So how many set bits, we're gonna check it directly. So if it is prime, so we're gonna update the result. Finally, we're gonna return the result. Now what is missing is that we just needed to finish this is prime check. So for I in raised 2 of integer of square root of the number plus 1, if n modular I equal to 0, we're gonna return a false. Otherwise, we're gonna return this number should be more than or equal to 2. Yeah. Now let me just submit it to check if it works and submit it. Yeah. The time complexity is dependent on. Yeah, as you can see, it works and it's pretty fast. So the time complexity dependent on the left and right. So the left and right is 10 to the power 6. So from here, this is 10 to the power 6. So what about is prime? Because for here, I bit count. So for this one, definitely this is 10 to the power of 6. It is a log 10 to the power of 6. Yeah, for this bit count. Maybe it is like 15 or so or something like that. And what about its number type? Its number is for how many bits? Yeah, so definitely the maximum number maybe 15 or something like that. The square root of 15. And here we're gonna use maybe 2 to the power of 15. What is that number? Maybe 10 to the power of 6. I don't know. Maybe. Yeah. So the final time complexity gonna be 1 times 10 to the power of 7. So it should work. Yeah. So that is why it works for this problem. You know, the left and the right is really big, 10 to the power of 6, and the right minus left is going to be a little bit lower. It's going to be 10 to the power of 4. Yeah. So this means inside of the range we're going to check left to right. So it's going to be 10 to the power of 4 instead of 10 to the power of 6. Yeah. So let's just recalculate it. So it's going to be 10 to the power of 4. This means from here. And then we're going to check the bit count. So for the bit count, it is 10 to the power of 6, log 10 to the power of 6. So this is going to be the final time complexity. Is prime. Let's just check the is prime. For this is prime, it depended on how many set bits. So the maximum may be 20. So the square root of 20. We're going to compare this one with the square root of 20, which is going to be the smallest number. Yeah. So this one is bigger, 10 to the power of 6. So the final time complexity may be 20 times 10 to the power of 6 and 10 to the power of 4, 10 to the power of 4. It is 2 times 10 to the power of 5. So this is going to be, the final time complexity. That is why it's so fast. So now we want to write another way. Maybe we don't like to use the Euler's algorithm. Maybe we like to write the asymptosis algorithm to check which number is a prime number. So let's just write it from here. So here I'm going to use E prime, and here I'm going to prepare a prime array. It's going to be false from the beginning times 2 plus true times n minus 1. So we're going to use the index to represent the number. So from here, we're going to change it to n plus 1. And from here, we're going to have an attack. If primes I, we're going to use another for loop for j in range I times I n plus 1 to the step going to be I. So from here, we're going to continue to write. Yeah, if prime, we're going to set it directly. So primes j gonna set to false. So finally, we're going to return this primes. Yeah. Now we're going to call this function from outside of the class. So the primes going to equal to e prime. And let's check the maximum number. It's going to be 10 to the power of 6, I believe. So 10 to the power of 6. Yeah, because it is not 10 to the power of 6. It is like something like 20. So I'm going to set it to 20. Maybe 20, maybe 30. I'm going to try a bigger number. Yeah, because because the maximum number may be 10 to the power of 6, but what about log 10 to the power of 6? It's going to be a small number. So here I'm going to use a 30. Definitely it's going to work. Yeah. I think I didn't prepare here, so I'm going to use. Let me just delete it. So I'm going to use the primes with this number n. Yeah. Now as you can see it works. Now let me just submit it. Yeah. Now as you can see it's really fast. But let's just analyze the time complexity. For here, as I said before, it's going to be 10 to the power of 4, but this one going to be less than 10 to the power of 4. Yeah, maybe the maximum of 10 to the power of 4 with 30. And what about the time complexity? It's going to be 10 to the power of 4. That is why it's so fast. I think that's all about it. Thanks for watching. See you next time.